One of the most important form of ordinary differential equations is the first order linear ordinary differential equations. And we will learn how to solve it analytically. But before doing that, I think it's good to have some motivation examples, such as what kind of physical model can derive a first order linear ODE. Okay, so one of the most important first order ODE is the linear one. And what's that form look like? So first order linear ODE can be written as y prime, which is as function of x, plus py that equals qx. So as you can see that the coefficient of the ODE will be either constant or only as function of x. Okay, so in that sense, when the coefficient is constant or only as function of x, that kind of form of the first order ODE is linear. Okay, the coefficient has to be either constant or as function of x only. And when the qx is equals to 0, this is called homogeneous first order linear ODE. Okay. And we will make several physical examples and to motivate the purpose of solving this first order linear ODEs. Why such equations are so important? One physical model can derive such linear ODE is temperature diffusion. Temperature diffusion. And we have that, for example, two subjects. One is T, temperature T, the other is temperature E, TE, which is the environment of the temperature of the surroundings. Then what we have is dT over dt. So the temperature as function of the time will be equals to HA divided by C, TE minus T. And this H is the heat transfer coefficient. And the C is the heat capacity. Okay, so we can rewrite this as the linear form, which is T prime plus KT equals KTE, where the K is HA divided by C. And you can see that this is a linear form of the first order ODEs. And similarly, we can have the concentration diffusion. And we can have a mixing box. For example, this is the concentration. The outside will be the environmental concentration. And this is a mixing process. And we should have similar form, which is dc over dt will be equals to k diff times ce minus c, and the k diff will be the diffusivity of the membrane. Okay, and you can see that since they are so similar, it can also write as a first order linear ODEs. And we can have other models, for example, the chemical kinetic models, which is we can also have another motivation examples, which is the chemical kinetics. And when we have chemical kinetics, you can think about d theta over dt equals to k theta, where k is the rate constant. And such form you can write as a desorption form. So this is a desorption kinetics. The surface coverage differentiate of the time will be equals to the desorption rate constant K times the surface coverage of a particular species, which is going to be desorbed from the surface. So there are, and also it's should be noted that this form, the theta prime minus k theta will be equals to 0. That is a homogeneous first order linear ODE. Okay.